In this experiment, we see how a vehicle, an autonomous vehicle, is managing to detect lanes, managing to keep lanes and move smoothly. It also identifies turns again via the marked lanes. It adjusts its steering accordingly and also doesn't move out of the lanes. In this experiment, we see how a lane or how a vehicle travels through a lane, identifies a parking spot and then parks itself autonomously in a given parking lane. Hello and welcome to this course on electric vehicles. In the next 2 weeks, we will talk about basics of control systems and how it affects control of electric vehicles. Okay, what is first a control system? Well, it's a interconnection of components that provides a desired output through a given process or a plant. Examples could be temperature control in a room, human body temperature, glucose levels in the body, speed governor in turbines. And if I am just looking at a vehicle, I am largely looking at a EV, I am largely looking at speed control of an electric vehicle. Okay, a formal definition is, so if I am given a plant with an output, let's consider plant here as an electric vehicle with the speed as an output and a reference speed, say I want to go at a desired speed of 60 kilometers per hour. What is a control input that generates, what is a control input to the car, the vehicle or to the motor driving that car, which will generate the desired reference signal or the desired reference speed. Okay, so in the example of the autonomous car, what you see is that one just can't guess the lane settings, right? It's not a trial and error, right? You including the steering angle and so on comes with some kind of an intelligence of how the car keeps lanes. It just looks left, it looks right and say I don't want to deviate from the lane. It also looks at turning and then it has appropriate turning so that it doesn't overshoot or it still keeps the lane and so on, right? As control engineers, our aim is to force the system to behave exactly the way we want them to. But then to control a system, we need to understand the system, right? How does the system behave under different situations? Why does it turn or how much steering angle should I give for it to turn safely and so on? And to understand it, we must represent it formally, right? So what do I mean when I say I must represent it formally? So let us try to understand this with the help of a small example, which is not related to electric vehicles, but something which is intuitively nice to understand. Okay, let us take this example where I have a single tank, where I have water flowing in and some water going out. And my control objective is to keep the level of the tank at some reference level, right? Say my desired height is h star. So what I have is, what I can control is how the water can flow in, how much water can flow into the tank. It's like adjusting tap and so on. It's like you can also look at it as if you are filling a bucket, but there is a small hole in the bucket. Okay, that small hole is represented through some outflow rate. Okay, the variable here is the height of the liquid which I want to control. I want to control the height of the liquid to some desired height h star. What do I know? I know I can measure how much is the height. If I am filling a bucket, my eyes can see how much is the level filling up. If not, I can maybe put up a sensor to see how much is the height. So I have the measured liquid level and maybe sometimes the measurements might be accompanied by some sensor noise, but for our purposes we can assume that there is no sensor noise. So when I say representation of a system, how can I look at it, right? How do I write it in a way which I can understand better? I can write a huge set of text which may or may not capture the entire behavior, but there is something better I understand, and that understanding comes from representing systems via a language called mathematics. Now if I look at this, so I have a variable which is height and it changes with time, right, based on how much is the inflow and how much is the outflow. Now what is easy to see is that if the inflow is equal to the outflow, then the height is constant. Now I know what it means to be, for a signal to be constant or a function to be constant, that is dh by dt is 0. Now second is, okay, if qi is not necessarily equal to q0, but say qi is greater than q0, then h will increase. An increasing signal is captured by dH by dt is greater than 0. Similarly, when Qi is less than Q0, the water level will decrease, right. So, the output is more than the input. So, we will assume, or it is natural to see that the water level will decrease. When something, a decreasing function is captured by dH by dt is less than 0. If both input and output are the same, the water level remains the same, right, and therefore dH by dt is 0. What causes a change in the height is when there is a difference between the input and output. If there is more input, less output, water level will increase. Less output or more output, less input, the water level will decrease. So, I can write this very neatly as what my mathematics teaches us, that H dot, I can write it simply as Q in or Qi minus Q out, and certain output which is just the height. So, here as I said, I will not really look at the noise, but the output of this particular system or this process is just the height which I measure. Okay, so how do I represent this? So, I can also write this as a set of signals Qi with a plus sign, Qo as with a minus sign. So, here I will have Qi minus Qo. Okay, this goes through an integrator which will give me H, right. So, I am just instead of writing dH by dt is Qi minus Q out, I will just write H is integral of Qi minus dt and some noise if at all present, and this will give me the representation which is kind of easy to understand via signals. Okay, good. Now, if I want to control this, the control problem here is to control the height to a certain level. A basic control logic would be to increase the flow when the system is below the reference, right. That is kind of intuitive, right. If I am here given Qi and Qo, I say just pump in more water. Similarly, if I am here above the desired, I just say don't pump enough water, I need some water to drain out. Okay. So, that is a simple control logic. Increase the inflow when the level is below the reference and decrease the inflow when the level is above the reference. It's kind of quite okay, right. So again, what is my control? I can only control the inflow. Okay. So, Qi is K H star, which is my desired, minus Yt. Okay. And what you see here is I can measure the output Y and then control it back to its desired height. Okay. Now, how do I account for the outflow, right? So, here what it means is that if H star equal to Y, then Qi is 0, which means I have this tank which I am filling till here. Okay. So, this is my, say, as some arbitrary Y, I have H star which is my desired. What I would say, okay, there is a difference between H star and Y. So, just open the valve and let water flow in. Okay. But I am not here accounting yet for the outflow rate, right. Okay. So, if there is outflow, then what happens? Well, my system literally changes to something like this. I add a feed forward term which takes care of the amount of water that is flowing out. So, Qi is now this, and I should also account for how much of the water is flowing out. Okay, this is in control language called a feed forward term. Okay, now I can simply write down the block diagram of this form. I have Y, I compare the actual height to the desired height, and based on the difference between, I generate a signal, or I open the valve so that water either fills in faster or fills in slower. So, this captures some very basic notion of a control system. What is the basic logic that goes into it, and how can I write it or even represent it in a little more of symbolic fashion. Okay. So, the next question here therefore would be, how do we choose the K, right? How much tap do I open? Typically, if I want to fill it fast, I say, okay, just let me open the tap to its full throttle. So, larger K, the tank will fill faster. Of course, it may, in signal terms, it may have larger noise amplification, and if I am looking at it in terms of a motoring action, if I am always running my motor or my scooter at the full throttle, it may lead to some kind of an actuator wear, right. So, that is something practically which I want to keep in mind. Is there a compromise? I just slow down the K, slower K is slower response, smaller noise amplification and less actuator wear, right. And then through this course or this couple of modules, we will say how to choose a proper gain, or is gain just enough, or do we need something more, or in general how do I choose a controller according to the specifications of the type of the plant. So, I am given a process and I am also told what I expect out of this process. Now, can I design a controller such that that process or the plant will behave according to certain given specifications. Okay, so back to how do we represent systems. So, whenever I talk of systems, if you come from an electrical engineering background, you may write down all your circuit equations as KCL and KVL, and in the earlier parts of this lecture we have seen how mathematically we can represent several of these DC to AC converters, AC to DC, DC DC converters and so on. You can write down the basic governing equations. Where do these governing equations come from? They come from, if I am just talking of simple circuits, you have your KCL, the Kirchhoff's voltage laws, Kirchhoff's current laws, and any other laws that govern the basic operation of these circuits. Okay. So, this will capture how the system's behavior evolves with time. What we will also see is, if you haven't had a background in control, we will do a very quick crash course on this. We will see how transfer functions also help getting a simple representation of systems with lot of hidden information. Okay. And then lastly, we will look at how state space representation is also useful in some different kinds of analysis and design. Okay. So, if I just take a simple example of a DC motor, how do I write down equations? So, I have an input voltage. If you just draw a picture, I have an input voltage, I have the armature resistance, I have the armature inductance. This will result into what we call as a back EMF. This back EMF is directly related to, if I have a shaft here, this will directly relate to the angular velocity that the motor generates. Now, there is also current component here. So, the first equation here will be V equal to R A I A plus L A D I A by dt plus the back EMF, and the back EMF is related to the angular velocity by this term Ke times omega. Okay, now the second thing is what generates a torque. The torque is generated via the armature current, and I think this is for now I do not need to go into the details of this. So, the torque will be Kt times Ia, right, and this torque which I see here will have to take care of the moment of inertia of the shaft. It also has to take into consideration the frictional component associated, and whatever remains will go to the load as the load torque. Okay, so now here I have two differential equations which govern the entire behavior of this circuit, and this is also what we call a mathematical model. And all kinds of understanding of the system, you want to do speed control, you want to look at efficiency, and all those problems that we solve while we learn our electric machines course can be simply represented by this model. Okay. Then there will be certain objectives. How do I generate, how do I deliver a certain torque or a certain power to the load at so and so efficiency or at so and so speed, and so on. Those could be the several control problems that could come into mind while we are looking at a system like this. So, the equations of the DC motor are ordinary differential equations. They are coupled, and sometimes equations of this form are not very easy to solve, or they are not very pleasant. Okay. So, what we will do here is we will quickly revisit the idea of a Laplace transform. Again, we will not do details of this, we will just do a quick introduction to this and how this will be, how the concept of Laplace transform will be useful for us to analyze systems and also design controllers in a much easier way. Okay. So, what I have is, if you look at system, say h of t, in general, if I am looking at it from the signals point of view, so I have h of t, I have the input as u of t, this is my h of t, this is y of t, right. So, y of t is usually represented by a convolution integral. Again, integral not very easy to solve. So, what we see is that with the help of Laplace transforms, the convolution simply becomes a multiplication. Okay. So, also we will define now the notion of a transfer function. Transfer function is represented as the Laplace transform of the output to the Laplace transform of the input, assuming all signals are 0. Okay. So, what is the Laplace transform? So, given a signal f of t, so the Laplace transform is defined in the following way. So, f of s, this is how we represent the Laplace transform in the s domain, where s is sigma plus j omega, it's a complex number, is 0 to infinity f of t e power minus st dt. Again, I will not do the details of this. So, a simple impulse function will have a Laplace transform of 1. A step function when I say it is a unit step function, will be of magnitude 1. So, ut is such that it is of number 1 for t greater than or equal to 0, and it is 0 for all other times. So, for that the Laplace transform is of the form 1 over s. If I have a t u times t, it is 1 over s square. A sinusoidal signal will have a Laplace transform of omega over s square plus omega square, and so on. Again, the details of this we will not do much. Okay, so first is, how do you find, given a system, how do we find the transfer function? We write down the ODE, we take Laplace transforms, and then we will see how it results in a linear equation. As an example, let me take a circuit where, say, I have a input voltage, I have a R, L, let's say I have a C, where I have the input is the voltage here, and say the output I am measuring is the output through the capacitor. So, I have a R, a L, a C, and a certain current flowing through this. So, what are the governing equations for this? So, I have V equal to I R plus L di by dt plus 1 over C integral I dt. So, I want to find out what is the transfer function of this. Let us say V out over Vi of S. So, I take the Laplace transform, this will be V R, the Laplace transform of I will denote as I of S plus S times L I of S plus 1 over SC I of S. Okay. So, now I have V is R plus SL plus 1 over SC I of S. So, what I see here, all the differential equations have now just simply become to me a linear equation. So, again, what is Vc here? Vc is 1 over C integral I dt. If I write it in the Laplace domain, Vc of S is 1 over Sc I of S. So, what I am interested now is to find out what is Vo, right? Vo or Vc is the same thing. Vo S by Vi of S. This is 1 over Sc I of S, that comes from here. Vi of S. So, if I call this as Vi, this is R plus SL plus 1 over Sc I of S. So, I am just left with 1 over Sc over R plus SL plus 1 over Sc. Okay. So, this is the transfer function of the system from the output from the input voltage to the output measured across the capacitor as voltage. I can also, nothing stops me from choosing current as the output. If I of S is the output, then the transfer function Vi S to I of S is R plus SL plus 1 over Sc. Okay. A simple illustration of how we derive transfer functions starting from differential equations. Okay. If I revisit the example of my DC motor, how do I write the transfer function? So, I write down the Laplace equations for this. So, the first, this will be VA is RA plus SLA IA of S. This equation in the Laplacian domain, assuming TL equal to 0, becomes J. Okay, so I will also have omega here, KE capital omega of S. Then I have J d omega by dt will become s omega s. This will be equal to kt Ia of s minus b omega of s. So, I rearrange these terms. So, I go, so this equation will give me this one, this equation can be written as this equation, and solving I get the transfer function from the voltage to the current as some expression like this. Again, everything just simplifies, so all the differential terms are gone, I just have expressions in S. So, for given set of parameters, for Ra is 2 ohms and so on, I can just write down the transfer function, very simple computations for this. If I instead take a standard mechanical system as equivalent to the circuit I did, so I have a mass, spring and damper system. The input is my force. Let us say the output I measure is my displacement. I can just write down the Newton's laws coming from F equal to ma, then some of them will be taken care of by the frictional forces, I have the spring constant and so on. So, I have these equations, and the Laplace of this will become x of s, I have s square m plus bs plus k is f of s, and I can easily write down what is the transfer function for this particular second order system. So, we will stop this lecture here. What we have seen so far is the general control philosophy of what is an objective of a control system, and then we also say, okay, so to achieve a certain control target, I want to have a good representation of the system that will help me design an appropriate control law. That came as a representation of systems as transfer functions. The next thing that we will do is to look at what we call as transient response and the steady state response of systems. That is coming up in the next lecture. Thanks for watching.